Now let's discuss the transformer tests which are used to find out the performance of transformer. Performance can be in terms of output, efficiency or regulation. Knowing the performance of a machine is very important because it will make us to choose a particular type of machine which is suitable for a particular type of load. So here, to know the performance of transformer, there are different tests conducted on the transformer. And the important tests that are performed on the transformer are open circuit test, separation of losses test, short circuit test and sumpness test. These are the important tests performed on the transformer to know its performance. And from this discussion on transformer tests, you will come to know why tests are to be performed on the preferred side of the transformer, and you will come to know why LPF wattmeter is used for measuring the power in open circuit test and why UPF wattmeter is used for measuring the power in short circuit test. Now let's discuss open circuit test. This test is performed to find the iron losses of a transformer and shunt branch elements R0 and X0. This is the electrical equivalent circuit of transformer and these are the shunt branch elements R0 and X0. So open circuit test is also used to find out the shunt branch elements R0 and X0 and to separate iron losses, that is to find hysteresis losses and eddy current losses. Now let's draw the circuit diagram to perform open circuit test. So this is the LV side of the transformer and this is the HV side of the transformer. Low voltage winding side is represented with LV and high voltage side of transformer is represented with HV. To measure the input power taken by the transformer, here we are connecting a wattmeter. This is the wattmeter which is LPF type wattmeter, and of this represents the current coil and this represents the pressure coil, and the terminals of LPF wattmeter are represented with M, L and this is C and this terminal V. And to measure the input current, MI type ammeter is used, and to measure the input voltage, MI type of voltmeter is connected like this, and the input power is taken through a single phase variac which can also be called as auto transformer, and to this variac AC input supply is connected. Let that be terminals phase and neutral. Here single phase variac is used for giving the required voltage to the transformer from the available input supply. That is, by varying this variac we can give the required voltage to the transformer. Here the important point that you must keep in mind is that OC test is preferred to perform on LV side of the transformer and HV is left open. As here one of the side of transformer is left open, this test is called as open circuit test. As this test is preferred to perform on LV side of the transformer means this test can be performed on any side of the transformer, but it is preferred to perform on LV side of the transformer. So in this test it will be also discussed what happens if we perform open circuit test on HV side with LV side open. Now let's see the procedure to conduct OC test. So the first step is connect the circuit as shown in above figure. Next, second step, apply rated voltage on LV side through variac. And the third step is note down voltmeter reading ammeter reading and wattmeter reading. And by using these values, find the shunt branch elements R0 and X0 and iron losses Wi. Open circuit test is very simple to conduct. Just you need to connect the circuit diagram like this, and by varying the variac, simply apply the rated LV voltage. And then upon applying the rated LV voltage, simply note down the ammeter reading, voltmeter reading and wattmeter reading. And by using these three values, find the R0, X0 and Wi. And the conditions that you must check before performing this test are that HV side is left open or not. And the second is use LPF wattmeter and use moving iron type ammeter and voltmeter. First, let's discuss why LPF wattmeter is to be used in open circuit test, and then it will be discussed about what happens if the test is performed on HV side with LV side open. Now let's discuss why LPF type of wattmeter is to be used in open circuit test to measure the input power of transformer. To understand that, it is important to recall the concept of ideal transformer, in which input power is equal to output power. As here in case of no load ideal transformer, the second circuit is left open, means the secondary current is 0, means the output power is 0, which means that in case of no load ideal transformer, as output is 0, which implies input power is 0, means the input power taken by the no load ideal transformer is 0. Input power is equal to output power is equal to 0. Whereas in case of loaded transformer will drag the input power at load power factor, which means in case of loaded ideal transformer, if the load is at 0.8 power factor lag, then the loaded ideal transformer will drag the input power at 0.8 power factor lag. These 2 points are very important to understand why LPF type of wattmeter is to be used in open circuit test and why UPF type of wattmeter is to be used in short circuit test. And here the question is why LPF wattmeter is to be used in open circuit test, and the answer lies in Phasor diagram. Let's draw the Phasor diagram for no load ideal transformer. If V1 is the input voltage, then flux phi will be in 90 degrees lag with input voltage, and as transformer provides the 180 degrees phase displacement between input voltage and output voltage, so E1 and E2 will be 90 degrees lag with flux phi, that is 180 degrees phase displacement between V1 and E2. And in ideal transformer, as permeability is constant, so current I0 and flux phi will be in phase, and this I0 is used for magnetizing the core, so I0 is equal to I mu. But whereas in case of actual transformer with excitation, the permeability of transformer core will vary, so I0 will not be in phase with flux phi, I0 will be out of phase with flux phi. And you can observe from the Phasor diagram that in case of no load ideal transformer, the phase angle difference between input voltage V1 and input current I0 is 90 degrees. So input power is equal to V1 I0 cos 90, as cos 90 is 0, which implies that V1 I0 cos 90 degrees is equal to 0, which implies that the power intake by the no load ideal transformer is 0. Whereas in case of actual transformer, I0 and flux phi will not be in phase. So the phase angle difference between input voltage V1 and input current I0 is less than 90 degrees. That is, in case of no load actual transformer, there is some power intake, whereas in case of ideal transformer, the intake power is 0. And now let's have a look on this open circuit test circuit diagram. So if you notice that here we are using LPF type of wattmeter in open circuit test. LPF type of wattmeters are used in the circuits with low power factors because they give the power reading with good accuracy for circuits with low power factors. Whereas to have good accuracy reading for the circuits with higher power factors, UPF type of wattmeters are used. And now, as in open circuit test, LPF type of wattmeter is used, which means that the primary circuit is at low power factor, and that you can understand by observing this Phasor diagram. So, as the angle between the input voltage V1 and I0 is less than 90 degrees, which means the no load power factor angle phi naught will be around 80 to 85 degrees, which means no load power factor is around 0.2 lag. That will imply that the primary circuit of no load transformer is at low power factor. So to have the power reading with good accuracy, we are making use of LPF type of wattmeter in open circuit test. And please make a note that the usage of LPF type of wattmeter in open circuit test is not because of the inductive nature of secondary circuit. As no load transformer primary circuit is at low power factor, we are making use of LPF type of wattmeter in open circuit test. If suppose load is connected, let the load be lagging load. So current I2 will be in lag with induced EMF E2. When load is connected, now the transformer will drag the extra current I2 dash. So now the primary current when load is connected is equal to I0 plus extra current I2 dash, which means the primary current I1 is the vector sum of I0 and I2 dash. As it is known that I0 is here, and if k is equal to 1, I2 dash will be in exactly opposite to I2. So now as I1 is equal to vector sum of I0 and I2 dash, so the resultant of I0 and I2 dash is I1, and the angle between V1 and I0 is no load power factor angle phi naught. And when the load is connected, now the primary power factor angle is phi 1, which is angle between V1 and I1. And if you compare the angle phi naught and phi 1 is lesser than phi naught, which implies that primary power factor cos phi 1 is more than the no load power factor cos phi naught. Means when the load is connected, now the primary power factor will improve. Therefore, as no load power factor is at low power factor, to have the power reading with good accuracy, we are making use of LPF type of wattmeter in open circuit test. Now let's discuss what happens if OC test is performed on HV side of the transformer. The point you must keep in mind that open circuit test can be performed on any side of the transformer, but it is preferred to perform on LV side of the transformer. And why it is not preferred to perform open circuit test on HV side of the transformer? To understand this, let's take an example. Let the HV side of the winding be 3300 voltage and LV side of the winding be 220 volts and the transformer rating be 33 kVA. So if test is performed on LV side and if test is performed on HV side, so on LV side the rated current I is equal to P by V, where P is the rating of the transformer and V is the rated LV voltage. Rated LV voltage is 220 volts. So that gives you 150 amperes. And now come to this case. Here the rated current on HV side is P by V, where P is rating of the transformer and V is the rated voltage on HV side. Rated voltage on HV side is 3300 volts, which gives you 10 amperes. As it is studied that an open circuit transformer will drag a current of 4 to 5% of full load current, which means in case of test performed on LV side, the rated current is 150 amperes. So 4 to 5% of rated current is, let us suppose 5% of rated current, which gives you 7.5 amperes. Whereas if the test is performed on HV side, the no load current I0 is 5% of 10 amperes. So which gives you 0.5 amperes. And here if the test is performed on LV side, the voltage that to be applied is 220 volts, which is readily available. Whereas if the test is performed on HV side, the rated voltage to be applied is 3300 volts, which is not readily available. And in this circuit we are making use of voltmeter to measure the input voltage. So if the test is performed on HV side, we need a voltmeter of range 3300 volts, which is not readily available. And coming to the discussion on no load current I0, if the test is performed on LV side, we got a current of 7.5 amperes. So as this value of current can be measured with the readily available meters, the accuracy is good. But if you come to the case of test on HV side, the no load current is 0.5 amperes and this value can't be measured accurately. Therefore, the following are the problems that we face if the test is performed on HV side of the transformer. That is, HV value input supply is not readily available and HV value range voltmeters are not readily available. And third, readings can't be measured accurately, that we seen in case of current, and therefore we get inaccurate results. And the fourth point is, as if this test is performed on HV side of the transformer, from the safety point of view, it is not safe to operate at that high voltage. Because of these reasons, open circuit test is not preferred to perform on HV side of the transformer. It is preferred to perform on LV side of the transformer. Now let's see how to find the shunt branch elements R0 and X0 from the open circuit test. With the circuit connection like this and by applying the rated LV voltage by means of single phase variac, note down the ammeter reading, voltmeter reading and wattmeter reading. So ammeter reading is I0 and voltmeter reading is V0 and wattmeter reading is W0. So observe in approximate electrical equivalent circuit of transformer that the current flowing through R0 is IC and the current flowing through X0 is I mu. So R0 can be taken as equal to voltage across that R0 and current flowing through that R0. So R0 is equal to V1 by IC and X0 is equal to voltage across X0 is V1 and current flowing through X0 is I mu. So X0 is equal to V1 by I mu. As here input voltage V1 is read by the voltmeter, so input voltage is taken as V0. So that is equal to V0 by IC and X0 is equal to V0 by I mu. So to find R0 we need to find IC and to find X0 we need to find I mu, and V0 is given by the voltmeter reading. So we need to find IC and I mu. For that, let's recall the concept of Phasor diagram, in which this is flux phi and this is voltage V1 and this is no load current I0 and this is angle phi naught. So the component along voltage is taken as IC and the component of I0 along phi is I mu. So IC is equal to I naught cos phi naught, and I mu is equal to I naught sin phi naught. So to find IC, we need to know I naught and cos phi naught. I naught is given by the ammeter reading, so we need to find phi naught to find IC, and phi naught is found by the wattmeter reading W naught is equal to V naught I naught cos phi naught. So W naught is known from the wattmeter reading, and V naught is known from voltmeter reading, and I naught is known from ammeter reading, which implies cos phi naught is equal to W naught by V naught I naught. That implies phi naught is equal to cos inverse of W naught by V naught into I naught. Therefore, as phi naught is found, place this phi naught in this. Therefore, power factor is known, and I naught is known from the ammeter reading, which gives you IC. So place this IC in this, and as V naught is known and IC is found, then we can find the R naught value. And similarly, to find X naught, we know V naught, and I mu is given by I naught sin phi naught. I naught is the ammeter reading, and sin phi naught is found by applying phi in this. So we will get I mu. Place this I mu here, and V naught by I mu will give you X naught. So this is how the shunt branch elements R naught and X naught are found from open circuit test. Now let's discuss how to find the iron losses from open circuit test. As it is known that total input power is equal to total output power plus losses. As it is discussed that the total losses in transformer is classified into major losses plus minor losses. As minor losses are very low, these can be neglected. And as this open circuit test is no load test, so output power is 0 because current I is 0, which means that output power is 0. Therefore, input power is equal to major losses, and major losses in the transformer are iron losses and copper losses. As it is discussed that copper losses depends on the current flowing in the winding and resistance of that winding. On secondary side, as it is open circuit, current is 0, so copper loss on secondary side is 0. As this is open circuit test, transformer will drag 4 to 5% of full load current. So as the current in the primary winding is 4 to 5% of full load current, so copper losses are very low, which can be neglected. From this, total input power can be taken as equal to iron losses. As here in no load test, wattmeter reads the input power taken by the transformer, and from this relation input power can be taken as equal to iron losses, which implies that this wattmeter reading itself indicates the iron losses of the transformer. This is how the shunt branch parameters R0 and X0 are found, and this is how the iron loss of the transformer are found from the open circuit test. Thank you for watching. If you like this video, please like this video, share this video, and do subscribe to this channel. Thank you. See you in next lecture.